Okay, so our next speaker is Sarah Palich-Heffern. She finished her PhD at the University of California, Los Angeles in the spring of 2016. She did her practicum at Los Alamos in 2015 and is currently teaching high school in Denver, which, as a parent of a child about to enter high school, means that to me she deserves a medal or something for that. So, Sarah?
So, as they were saying here, I actually finished last year in the spring, and unfortunately I missed last year's conference because I was in Australia enjoying all the awesome koala bears, which is why my computer is covered with koalas. So anyways, I'm going to be talking to you guys, basically giving a mini summary of what my dissertation talk was. Be aware that it has been a year since that, and I have been teaching 150 high school students every day. So if you have particularly deep questions, you might have to go to the papers. Okay. So my graduate research was in the geology department at the University of California, Los Angeles. So my work was sort of most related to carbon because it was funded by the Deep Carbon Observatory, and most related to how carbon acts in the deep earth. So I was a mineral physicist, which means basically we look at the minerals that are in the earth under extreme conditions, or the conditions you'd find underneath your feet, down in the mantle and then close to the core. So I ended up doing a lot of carbon research on many different minerals, so we'll go into some of those. Basic sort of carbon debrief. Carbon's recycled at 10 to the 13th grams per carbon per year, so that's just the recycling that you get through volcanic action and subduction. What I was looking at wasn't just that carbon that was coming down and then being recycled back into your atmosphere. So I wasn't looking at that global carbon cycle. I was looking at the deep earth carbon cycle. So how carbon would act if it were able to make it all the way down and be subducted into the mantle. So the motivation for this is understanding how CO2 and carbonate specifically act under extreme conditions, not only on the Earth, but on exoplanets and other planetary bodies. The work that we do here was able to be used in modeling because we come up with equations of state using pressure, temperature, and volume information. So pictured here is a diamond anvil cell, which I have more about on the next page here, where all of my work was done, regardless of where on the planet it was done, was using diamond anvil cells called DACs. And we're able to reach really, really high pressures using diamond anvil cells with a minimal amount of force. So if you think about it, if you're pushing down on your hand and you're just using your other palm, you can push pretty hard, but it doesn't hurt a lot, okay? You don't actually have a lot of pressure going on there. Now, if you take your fingernail and you dig it into your hand, you're gonna have a lot more pain because there's actually a lot more pressure because your area is smaller. Same principle applies to the diamond anvil cell. We have very small tips to the diamonds that we use, between 300 microns up to, I think I used 500 microns. So those are able to then create large amounts of pressure with relatively low force. So you're able to tighten these cells using your hands, which is really great. They're also pretty small and very portable. So you can take them with you to any of the sources where you need to get your information. For me, I was mostly using synchrotron sources and then spallation neutron sources. So I did work at Berkeley, Argonne, and also Oak Ridge in the United States, and then Grenoble in France at the European Synchrotron Source. So essentially what's happening is your light rays or X-rays, depends on what you're doing, or your neutrons, if it's a neutron experiment, come in, and you have a very small amount of material there, okay? And you just essentially have micrograms, and you're able to, using that small amount of material and using the high energy from your X-rays, be able to see the structure of that, either single crystal or powder. So the first project I did, which is now from 6 years ago, is on the mineral Hanksite. It's really rare. It's honestly not going to make it through the subduction process. It's a salt, so when introduced to water, it would disintegrate into its constituent ions. But we're interested in looking at how carbonate and sulfate groups acted under high pressure. So we decided it was going to be a pretty good chance to explore a complex and large ionic salt. So we took this to Berkeley and we compressed it to about 18 gigapascals, which is the scale that we use when we're talking about pressure inside the Earth. So down at the core mantle boundary, you're at about 320 gigapascals, so really, really high pressure. We only generally, in my experiments, go to the transition zone, which is about 600 kilometers down. So we're talking about 60 gigapascals maximum. And we were able to, get some of the first, modern, the last time this had been done was in the early 1900s, data on Hanksite, the mineral. And then we're also able to look at an equation of state, just volume and pressure, no thermal component to this, for Hanksite. The Hanksite one is the circles here, and then the tychite one, which is another very similar but cubic mineral instead of rhombohedral, and it is here. So essentially, when you're looking at these curves, you have pressure going out on the bottom and volume coming out on the top here. It's normalized to the to the original volume on here, not always. You'll notice that these are like the exact opposite axes that are commonly used in chemistry textbooks. So you kind of have to flip your mind around there. But essentially, if you have a larger bulk modulus, you're going to have a stiffer material. It compresses less. If you have a smaller number, then it compresses more. So in this case, we can see that tychite is less compressible than Hanksite. And then you also see this drop in the data where we have the, I think it's about 10% drop in volume, which shows some sort of change. It, in fact, was not a phase transition we found, but rather a sort of more squishing, I guess you could say, of the ionic materials inside. We also did a Raman experiment on this in our lab. It was the last time our Raman system ever worked, so it was pretty good to get some data out of it. And you're able to see that depending on the location in Hanksite, the two different sulfate modes, which are this peak starting out right here, actually separated and vibrated differently depending on where they were and what other ions they were attached to, which makes sense, but was pretty cool to see. Essentially, this was just a first run at understanding how carbonate worked, taking a look at high pressure, high temperature, and determining equation of state. Next project was dolomite, which is a sort of sister to calcite and aragonite, but has two ions in it. So we have both manganese and calcium with a trace bit of magnesium there. And this was more motivated by the interest that somewhere between 40 and 100 gigapascals, so somewhere in the mantle, there is proposed to be a transition in the coordination of carbonate. So it's going to go from 3-coordinated carbonate here to a tetrahedrally coordinated system. And we're interested in where that happens and how that happens. So just pictures of here, this is an SEM image showing some of the inclusions and impurity, which is rhodochrosite, which is the state mineral of Colorado, if you're interested. Essentially, we had equation of state data here, and we were able to extract bulk modulus. Depends on if you go to third order or second order, but we were able to find a bulk modulus between 85 and 110. We were not able to, in this particular run, see any change in the carbonate groups. Then we're able to then go from powder diffraction, and then we spent a summer at ESRF in Grenoble and added a lot more consistency to our data with a lot higher accuracy. Notice the error bars for the powder diffraction are fairly large, and the error bars for the single crystal are smaller than the symbols. So we were able to verify that our initial experiment was correct and add a bit of the first data taken for the equation of state. Now, continuing on that same sort of strain, we had an aragonite experiment. We ran this one at ESRF as well in Grenoble, which is European Synchrotron Radiation Facility. And once again, we're looking at that same change. We're looking at this planar carbonate into the tetrahedral polyhedral coordination. And this time we only ran single crystal, and we went up to about 40 GPa. So this was the picture of ESRF. If you haven't been, try to make it there. Beautiful Alps in the background, get to wake up to every day. Yes, fantastic. And many common espresso breaks after each run. Got to go get your espresso. So this study shows on top of the blue is from several previous studies, and our data is the black on top. One of the great things about mineral physics is if you get the same answer as somebody else, that's really great data, and you should publish it. So it's one of those few fields where you actually get to build on each other, and you really, really, if your data matches perfectly, that's fantastic. We're just building a stronger and more constrained equation of state. So we're able to see that our data was very well taken at almost 1 to 2 GPa increments, all the way up to 40. And that this was able to get a very precise bulk modulus of 66.5. And then this is the pressure derivative of the bulk modulus. Another cool thing that we saw when we were looking at the aragonite is since we were doing single crystal, you could really hone in on atomic positions. And we're able to notice some major changes in the axes. So this is the C axis, crystallographic axes. You have A, B, and C. And this is the C axis to the A axis versus pressure, and then B to A, and then B to C. And you'll notice on these graphs here that you have pretty continuous trend up until about 30. And then something else starts happening. And same thing here, pretty consistent linear trend, and then your slope changes. The most extreme case is this B to C, where you're kind of coming around, having a rebound effect, which is interesting in and of itself, but then you really start shooting upwards here. And what we interpret these results to be is there's a proposed phase change, so a change in structure for aragonite at about 40 GPa. We think that we are seeing the beginning of that transition. Okay? So that supports the data from other groups that believe it happens at about 40. There was no heating in these samples, so there could be kinetic effects that are holding back transitions as well. So we may be seeing straining do that. So just to give you an actual visual picture of this, this is the 0 GPa structure. You can see the axes here. C is going up, B is going this way, and A is coming straight out towards us. And you can see that the unit cell size has decreased, and more in the B than in the C, which accounts for some of that curving that you were seeing in the previous slide. And then finally, we had previous thermal data that was taken at the Italian synchrotron that we were able to combine with ours and basically just verify that our data fell atop previous data. Great part about this is the paper that we were able to publish on that gives you all the tools to create a comprehensive equation of state that can be used in planetary modeling for aragonite. Okay. Now, my final project that I'm talking about here is kind of like my baby. I love this. It happened while I was just sitting down with one of my professors one day. We were thinking, what could we do where we could use the Spallation Neutron Source at Oak Ridge? What could we do? We're like, hey, CO2. Has anyone done a lot on CO2? All of our funding is for carbon. We can definitely make this happen. So we ended up doing the first resistively heated diamond anvil cell in a neutron beam experiments ever. So we wanted to, in terms of the science motivation, understand this phase diagram of CO2. We always put quotes around this because this isn't concrete. This hasn't been proved. And honestly, in our experiments, we've been seeing that these lines aren't always true, which means this is more of a map of what people have seen than a real scientific phase diagram. So I wanted to explore this space, and specifically, we were looking at CO2-2 and CO2-4. As I said before, we are the first successful users of this, and I just love that I was able to put together a coalition of people from the DCO, from Oak Ridge, and then from UCLA, and basically run this project myself. So Oak Ridge, another beautiful place to go. Essentially, we created quite the contraption. This is a membrane press, which works on a diamond anvil cell, which is a little elongated from the one I showed you previously. It just gives you larger windows, which the neutron diffraction needs to be able to gather the data off of the detectors here. And then we were able to put our sample in here, and then we actually put just two very sort of brute force heating copper heaters on the top and the bottom. And we were able to get our temperatures up to about 625 degrees. As of late, I think the highest they've gotten is about 700. So it's pretty good. So we went up in pressure first, then we went up in temperature, and then we actually took data as we quenched on the way down. Okay? And we found out that CO2-4, if you convert to here, is stable all the way back down at long times. So it takes about 8 hours for the neutron experiments to run, because neutrons are less plentiful than X-rays and more highly penetrating, so you need a longer time. And CO2-4 is stable all the way down. We also found that evidence points to it being a linear molecule in this state instead of bent. There's a whole debate on that, which we won't get into. And then also we're able to generate some equation of state data for CO2, bulk moduli up here, depending on if you're doing second or third order. So essentially, all of my projects were able to come together and tell us something about the structure, stability, and thermodynamic properties of carbon in the deep Earth or in deep exoplanet or whatever other planetary body you wanted to do. Okay, so the last bit that I have here that I want to talk to you guys about, I'll come back to that page. It's actually a little more personal and close to home from what I've been doing last year. And I thought I'd put it in here because this is a great opportunity to talk to a lot of really smart, really awesome people who can make a big difference. So just up here is a little bit about the school that I was teaching at last year. So I was teaching at a public school, normal high school. Can I get a show of hands for a number of people who attended a school that was 1,500 or higher in terms of population for high school? Okay, so those are pretty big schools. And it's hard for everybody there to know everybody. And it's hard necessarily for, like, say, the counseling department to know everyone. I was at a very similar school in Aurora, Colorado. And we were a school which has innovation status, which means that we were able to do things differently than necessarily mandated by the state, and we had a little more freedom. And I had student taught there the year before, and it had been a fantastic experience. It had been one of the best. And this past year actually was probably one of the worst experiences I've ever had. And that was kind of due to a lot of factors combining together to create a lot of pressure on a school that it just couldn't deal with, especially in the current funding environment. So this is just a bit of the statistics for the Aurora Public Schools. This is for the high schools. Saying class average size is 24 is kind of misleading. You have a lot of opt-in sort of choice classes in high schools that are small, say 15 to 20. I was teaching 9th grade physics, which is a core class. So my classroom size was about 36 kids. Okay, so 36 freshmen, having to learn physics without doing any algebra. Yeah, so they didn't actually know basic algebra, so we did a lot of conceptual things. Say you'd go through Snell's law, and instead of talking about n1 sine theta 1 equals n2 sine theta 2, something that's kind of really basic for those of us who've taken physics classes, we would be like, okay, so imagine you're driving a car, and you're going from mud to dry road. What way is your car going to pull when you go in at an angle? And that analogy holds, and so that's how we taught them which way light would deflect. So it's very interesting and sort of different perspective on how to bring physics to kids without the math. Let's say, we didn't really have a high gifted and talented population at all, and basically all of our kids, more or less, are on free and reduced lunch, which just means we come from low-income families. A lot of them come from trailer parks or sort of multi-housing units. So one of the issues that the school was definitely running into, and Colorado is not the best at this, they don't fund their education the best, is that the district and the state give a certain amount of money per pupil, and that's true pretty much across everywhere in the United States. And so our school was running into the issue of, okay, we need more students to get more money, but we don't have the current resources to be able to pay for that. We don't have the right admin or disciplinary people. We don't have enough counselors. We don't have enough psychologists to really deal with the true deep issues that our kids are going through. And if you look up here, national average for spending per student is about $12,000, okay, more or less. And then Colorado's down at, about $10,000 per student. Currently, actually, this fiscal year, we're down at $7,600 per student. And Lowe's, as gives you, is, let's see, we'll do the per pupil revenue, which is here. Lowe's about $7,000 in Idaho at this time. And then high, you look at New York, okay? Massachusetts, places that are getting testing scores that are higher than those coming out of international countries. By state, Massachusetts is almost like the top country in the world in terms of testing. So we're running into a real funding issue. And some of that came from the fact that when 2008 happened, there was a lot of budget cuts, right? Everybody's really familiar with this. We're feeling this in science too. But since then, education hasn't been brought back into a lot of budgets. It hasn't been re-upped, okay? So in comparison, we're actually spending less on education now than we were in the 90s, okay? Actually less. So the two ways that you as voters and communities can change things is there is a bond issue, which basically just means we're gonna cover capital costs. So schools are falling apart, we need new facilities, we're outgrowing, all that's covered by bonds. And then mill levies are basically what you are able to do to create revenue for teachers' salaries, for classroom supplies. So they're two very different things. And the school I was at had a state-of-the-art facility. They'd opened in 2010. The school was beautiful, but we were running into the inability to have enough money for the classrooms. We were operating on computers that were from 2010. They often wouldn't log in or wouldn't operate. I had a whole project with my students where they were so frustrated they quit because it took so long to log into a computer. Okay? Now, I'm transitioning next year to a charter school, so I figured I'd put a little information out there. In most states, to be honest, charter schools are required not to be for-profit. There are several states that have a lot of for-profit, Michigan being the top one there. And in most places, charter schools are actually a really great thing. But once again, you have to do your homework, make sure that your local charter schools are supporting your local community, because you want them to have the same distribution of students that your regular schools do. And all they're gonna have is a greater flexibility to use the funding that they get and also occasionally the ability to augment their funding. So the school I'm transitioning to got a lot of money from Oprah Winfrey, okay? So they're able to actually provide their students each year with a computer, which is just a world away from the troubles that I've been having over the past year. And then I'm gonna end with, we're all really intelligent, fantastic people in this room. And I think we owe it to our communities to make sure that we're involved and to make sure there isn't that feeling of the scientists are above or other. To like, I don't believe research. They're saying coffee is good for me one day, they're saying coffee is bad for me the next day. How can I believe that? Well, if you're face to face with a scientist, they become a person. And once they become a person, you start understanding, and your kids in your community are gonna be better for it. So please go out, coach a team, do outreach events, make sure you go to town meetings. If you have kids, go to your PTA meetings, please, okay? Interact with your communities, and also, above all, make sure you're really paying attention to what's on the ballot and what you can do. Call your legislators, call your city council members, call your school board members.